we can start. We are in time. And Rosine will show us in his session something about memory corruption, memory analysis. I think it's a hardware hack. I don't know exactly. I'm interested in this, so I stand here. And let's start.
Thank you, mate. Before we start, I will actually ask you to give a big clap to the organizers, because I think they're doing an amazing job, and I'm very happy to be here with you today. All right, so we're going to talk today about memory corruption bugs and how to automate the process. To be fully honest with you, we released the tool like 3 months back, and we got more than 10,000 downloads. And every single question I got was regarding remote Stack Overflows, which is something the tool was not meant to do. Like, the tool was meant to automate exploitation of invalid memory writes, and not at all, Stack Overflows, which I thought, is pretty well understood. Like, come on, it's the first class of bugs which was disclosed, which actually deals with memory corruptions. If you Google for memory corruption bugs, like, everybody and his brother wrote a paper about Stack Overflows. So I was kind of bored about Stack Overflows, and I thought, like, come on. And then I thought a bit about it, and eventually there are actually quite a few new security mechanisms, like Fortify or PIE, Position Independent Executables, which actually worth a look. So if you guys agree, I'm going to start with this, and then we'll switch to the meat, which is how to find and how to automate atomic or not so atomic, so like overwrite, in any other section of a binary. You may see by now that I'm not a native speaker, and I'm pretty sick today. I'm actually coming from Australia. Anybody is coming from New Zealand? All right, so I'm the one coming from the opposite side of Earth, and I got pretty sick in the plane. So if at any point in time you don't understand what I'm saying, please interrupt me. Like, you can scream or wave around and stuff, and I'll be very happy to rephrase my wording or reword what I'm saying. Let's do it. Anybody read the white paper? Yeah, man. Hey, you guys have any idea how much time I spent on that stuff? And there is one dude who actually read it. Come on. At least lie to me. Tell me everybody read it. Yeah. Thank you so much. That's some love. I love you too. All right. So, that's not really important. The only point which is actually relevant to me that I'm very happy to be here. And we're trying to create a small security conference in Paris. It's called hacktivism. It's not too far, and it's pretty. It has some quality. So if you guys like my talk, please submit. Please come. We'd be very happy to see you guys in Paris. All right, why doing binary stuff? Because to be fully honest with you, in my daily job, I don't enjoy web application that much. It's super repetitive, and I think the whole binary thing is a lot more complex and more exciting and more. That's the meat. Agenda. So I go back to a few basics. If it's too easy, you please raise your hands, and I'll be very happy to skip the basics and go to the meat. I have like 95 slides. There is no way it's going to fit in 1 hour. Yeah, I'm going to be late. Sorry, guys. So if it's too easy, let me know. I'll be more than happy to skip. In a nutshell, the tool is available. It's free software. So the address is pmcma.org. Yeah, I know the name is pretty strange, but whatever, it was available. Surprisingly. It's published under the Apache 2 license, so it's free as in free software. We also have a repository on GitHub, and people actually do submit patches. So if you want to improve the tool yourself and add new checks and stuff like that, feel free to do so. We're very happy to merge new patches. If you do that, please use the GitHub. It's a lot easier for us in terms of maintenance. All right, so like I mentioned earlier, we got 10,000 downloads for a tool which is actually helping reverse engineering on Linux. So either some guy is psychic or is using a bot to download it all day long, or the tool is actually interesting. This is like way more than we actually expected. So what is the tool supposed to do? The tool is actually a debugger. It's ptrace based, so much like GDB, but it does all the stuff that GDB cannot do for you. And in particular, whenever you can trigger a bug. Say you've been doing some fuzzing session or something, you got plenty of crashes, and you'd like to analyze which one are actually exploitable and which one irrelevant. The tool is here too, so it's not writing an exploit for you, but it's showing you exploitation strategies, what we call exploitation scenarios. I'm going to start with a demo, because so we'll all be on the same page. So, any questions so far? Okay. Okay, so I'm starting the tool. I cheated a bit. I created a small script. What it does is just starting Perl and filling it poc1.pl, which actually triggers a null pointer dereference. Yeah. Full size. Yeah, doable. Font size. Font size. Doable. Is that more sexy? Yeah? Kinda? Everybody can read? Yeah, all right. Okay, so this is just a small null pointer inside Perl, but at least, yeah, any question? No? Okay, so at least we'll be on the same page on what the tool does and how it works and stuff. So you have different ways to invoke it, much like GDB, you can attach to a running process, or you can start a new process and start debugging it. So it shows you a bunch of stuff, blah, 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 like the command line, which you can retrieve from the stack, like which instruction it failed on, the state of registers, that's not too exciting. Then, okay, what really starts to be exciting is that it tries to analyze the root cause of the bug by looking at the registers, looking at the instruction, and the state of the stack. Basically, if you can walk back the stack, you know the stack is not mangled, so it's not a Stack Overflow. You received signal 11, so you know it's like, some kind of invalid memory dereference. And by looking at the registers, it's pretty easy here to say that it's a read operation because it's only comparing and not writing anywhere in memory. And it's actually failing because EBX, which is worthing 0 at this time, is actually pointing to invalid memory. Do you have any kind of laser pointer or something? If anybody does, that'd be sweet. No? Okay. So the EBX plus 8, if you have EBX within 0, pretty obviously it's going to try to read from the first page, which is never mapped under Linux. Thing is, if you don't know assembly, if you don't know all that stuff, the tool tells it for you in human language. So that's pretty sweet. It's much like, Bang exploitable for Microsoft or whatever. Then it looks at a bunch of binary properties like, was it compiled with PIE? I get back to this. Stack cookies, Fortify, a bunch of properties like, is it a C++ binary, for instance? It's kind of relevant because if you have a C++ binary, you expect to find heaps of function pointers. Why? Well, because every class is basically, when you invoke a class in C++, what you actually do is calling a function pointer, right? So, well, it's pretty interesting to notice. Okay, then the real thing, it checks. Right, ASLR is tough. It's, when we're actually writing exploit, repeatability is a problem. And so ASLR is, at the core of the defense mechanism under Linux. How do you check ASLR? The idea is that the tool is going to respawn the very same application 100 times and look if the mapping of every section differs from a run to the other one. All right? You could say, hey, I'm going to do that with static analysis by, looking at the binaries, PIE or whatever. If it's not, you expect the main binary to be mapped always at the same address, and you can make a wild guess regarding shared libraries. It's actually much easier to just re-execute the binary and check in practice if it works or not. I got some surprises, like on some pretty old kernels, the libc, for instance, would be mapped 10% of the time at the same address. So 10% is a lot. I mean, if you're doing if you can attack at will, meaning you're attacking, say, a server, and it's forking, so you can trigger the bug as much as you want. In 10 times, you're sure to get a shell. That's a lot. So you want to see it. So it's interesting to see it in practice. All right? Okay. Then we check, much like PAX test, the regression test for the GR security and PAX inside GR security kernel. We check, like, is the stack executable? Is the heap executable? This is entirely dependent on your kernel only and not the application you're attacking. But it's worth noting, and it's always something you got to check before writing a proper exploit. So here I'm using a random latest Ubuntu machine or something. So like by default, the mappings are not executable. I mean, what's writable is not executable, but if you call mprotect, then you can. Is it always the case? Of course not. If you use GR security kernel, for instance, you can have a hardened configuration, which is going to prevent you from executing anything on the stack, even if you try to mprotect it. Basically, the call to mprotect is going to fail. But Ubuntu is like not that good. Okay, then what the tool does is trying to get is basically parsing every writable section and looking for function pointers. If we go back to the definition of a function pointer, it's something which is going to be on a writable section, and it's something which is pointing to executable memory. So by parsing all the writable memory, we can actually get a short list of all the possible function pointers inside the application, even if they're stored, say, in shared libraries. And people tell me, oh, but I do that manually. Hey, you know what? Bullshit. You're never going to find a function pointer in, say, the data section of libcrypt, right? And even if you do it statically, some tools are here to do this, like mona.py. Anybody's using this? It's a cool tool from the guys from Corlan. Thing is, it's only static, and there is a massive difference between a function pointer being somewhere in the address space, and from a given point in time, this particular function pointer being called, and this is what I'm interested on. I don't care about finding function pointers which are not called during the normal flow of execution. Any questions so far? Too easy? Yeah? Okay, he's asking me if mona.py is available on Linux. No, it's not available on Linux. Yeah. But it's like the state of the art, so it's a good benchmark. Then we try to see if, basically the tool is checking if after the crash, we're getting back to the same instruction. This is pretty relevant. Why? Yeah. Right. The main idea. All right, so for those not in the room, yeah, they're saying that the probability, yeah,
It's hard to be in the loop.
is high to be in a loop. Actually, it depends. Like either, so in the case of my comparison here, you know, are you gonna get back to the very same instruction with the very same set of registers? It's hard to predict. Like, you know, basically arbitrary computation may happen, and I have no idea. The thing is, if we want to distinguish between an atomic write, which failed, and another write, which failed. If I can overwrite multiple times, like overwrite an entire section, it's a lot more interesting to me than a single atomic write somewhere. Because if, for instance, if I can overwrite the whole heap with content I control, it's a lot more interesting to me than writing, say, 4 bytes somewhere in the heap, especially in case of ASLR. I'll get back to this. All right, and then from then, what the tool does is basically looking for function pointers. Okay, in this case, it did not find any. Wow, that was a cool demo, right? Okay, so people asked me about Stack Overflows. So I'll do the Stack Overflow stuff. If it gets boring, please, we'll get back to the meat. Boring, yeah, I know, but like, I got questions. Now, there is actually some pretty cool stuff to say. Anybody knows how to bypass position-independent executable, for instance? Okay, position-independent executable is the fact of having full randomization. Let's see that. Okay, so basically, Stack Overflow, blah, blah, blah. So you have a bunch of possible, I mean, compared to the very first articles like Aleph1 and stuff like this, we got non-executable bits, we got stack cookies, we got ASLR, position-independent code, possibly static GOTS, and ASCII armoring. The real point why I'm saying it's not that interesting is that you can do the whole analysis and write your exploit statically. You don't need a debugger to do that. And I'm going to prove it to you. SSP. So that's the main difficulty when writing remote Stack Overflows. This guy, Ben Oakes, is a really, really sharp guy, in addition to being nice and being Australian. Yeah, tough life. So he showed at this conference in Australia, which I really recommend to you, which is called RockScan. He showed that basically, when you develop a server under Unix for to make the whole design more robust, what we do instead of using threads, because we could use pthreads, much like those, you know, those Windows morons. Now, what we do is actually forking, because it creates another process, and like, we won't have 2 threads trying to, you know, write in the same memory, triggering rest conditions or whatever. So what we do is actually creating a replica of the parent process by calling fork. When you do this, the forking process is going to inherit its stack cookie from its parent, because you're not calling execve, which is the only system call which is setting the stack cookie for you. So every single fork is going to have the same mapping. In terms of ASLR, it's going to be the exact same mapping. And the stack cookie is going to be the same. So what Ben said is that, hey, you know what? I'm going to overwrite byte per byte the stack cookie in different threads. So like, I create a new connection. I send the amount of data to fill in my buffer, my stack buffer. And then I'm reaching my canary. I'm overwriting only the first byte. I have 256 tries. And after 256 tries, one of them is actually going to succeed. And that's going to give me the first byte. So byte per byte, you have 4 bytes, assuming a 32-bit architecture. So in 1,024 tries, you can actually brute force the stack cookie. Yep. Well, that's pretty bad. All right, the second production, honestly, stack cookie was the absolute nightmare for everybody until pretty recently. 45 is like a new compiler enhancement. Basically, at compilation time, they're trying to replace, say, memcopy, which could be vulnerable when writing to a stack buffer to a Stack Overflow. So they're going to replace memcopy by memcopy_chk, which takes an additional argument. And the additional argument is the maximum size of the buffer, assuming it can be known at compilation time. And it's going to check at runtime that you're not trying to copy past the end of the buffer. If you look at the implementation of, say, memcheck_chk under Apple, it's scary. It completely sucks. What it does is verifying that the length you're giving at runtime is smaller than the actual size of the buffer. But it's not verifying that the copy is starting from the start of the buffer, saying that if you have a buffer of 20 and you're starting the copy in the middle of the buffer of a size of 20, it's actually going to say, hey, it's all right, man. Let me show you something really cool about 45. I love it. I call it 40fail. Right. Anybody can see what's the problem with this code here? Well, it's pretty legit. And if I ask GCC to compile it, so I'm going to use the 45 flag. I'm going to ask you guys a favor. Can anybody bring me a beer? Is this drinkable water?
It's only water.
It's only water. All right. I shall survive. Right, so depending on the exact version of your compiler, 45 may be applied by default if you use optimization of at least 2. If you use optimization greater than 2, you bang stupid because it's not supported by GCC anyway. All right. So if I do this, GCC gives me a warning, but it does compile the thing. And if we look at the dynamic symbols inside the newly created binary, there is no memcopy_chk whatsoever. So here, 45 actually failed, and it did so because it could not find the definition of memcopy. This is super bad because if you take a binary like SSH, you will find both memcopy and memcopy_chk, which is actually expected because 45 cannot protect every single call to memcopy. It only protects those who actually copy to a static buffer with a known size in the stack. So if you copy data in the heap, or if the size of the buffer is not known in advance, then it's totally unable to protect the binary. Thing is, in SSHD, imagine that one of the objects is actually using memcopy to call, to copy data to a static buffer in the stack. If one of the objects actually failed to include string.h, like in my previous example, you're totally unable to see it. Thank you, man. I love you. Right, so the problem here was actually that my definition of memcopy was missing because string.h was not, was missing from my demo example here. But, you know, is it happening in SSH? Well, hard to say. All right. Oh, is that? Okay, so he's asking me if memcopy here has length checking. So in the example I compiled, not at all. Like, it completely failed. Like, if you look at the symbols inside the binary I did compile. If it had this additional length check, you would have memcopy underscore chk. All right? A little bit more what? Larger. Yeah, sure, I can do that.
So if I have this memcopy without the check, there should be code around that does the range checking for the memcopy. Otherwise, it will fail if somebody puts too long data.
I didn't get you, excuse me.
So you say memcopy inside the code of SSH
Yeah.
somewhere.
Yeah.
SSH needs some range checking code before it starts memcopy. Otherwise, it could fail.
So I'm not saying that SSH is actually vulnerable to anything. I'm just saying that it's impossible to verify that Fortify has been applied to every object which has been used to create the big SSH executable. And if you look at, if you compile every single network daemon available on Linux, you will probably find heaps of vulnerabilities of that kind. I mean, missing checks like this. And you can credit me for your advisory. No, I'm kidding, I totally don't care. All right, so the big thing is PIE, which stands for pi. Come on, no. Yeah, position independent executable. The main idea is that even though we have ASLR normally, your main binary, unless you compile it with these new fancy flags, is not actually going to be randomized. Meaning your shared libraries may be randomized, your heap and your stack are going to be randomized, but because at compile time, the compiler is assuming that the base address of the main binary is going to be static, it's going to hardcode all the references to other sections, like to data sections, to BSS sections, any internal section in the binary. And therefore, you cannot change the base address of, the main executable, which is pretty bad. Even if you have randomization, and you don't have PIE, you have a lot, in case of Stack Overflows, you can find ROP gadgets, for instance, inside the main executable, because the PLT is going to be at a static location. Just a sec. So if you want to do return to PLT, or if you want to do ROP, you can find your gadgets at known locations. Yes?
We got a question. So what's with 11.10?
What with 11.10? Yeah, it's going to work with 11.10, but my version is 10.10. It's usually, if you have this feature on 10.10, yeah, it's going to be on the next versions too. Good question. Thank you much. So if you look at public exploit, I honestly could not find a real exploit for PIE. Well, he wrote one, but he failed at the compilation phase. You want to come on stage and discuss this? No? Okay. All right. So thing is, if you compile with PIE, the main executable is going to be compiled much like a shared library, and it can be mapped at any address, so it can be randomized too. And then exploitation becomes a problem. Yes, it does, because even if you have an exploitable Stack Overflow, and you can return anywhere, you control the stack and whatever, what do you return? You have no idea. Good news is I found something for you. The main idea that, okay, if we keep in mind the layout of the stack, so you're going to have like the buffer you're going to fill, then you have your stack cookie that we know how to brute force, then we have the saved EBP, and then we have the saved EIP. The saved EBP is not that relevant, but the saved EIP is like, if I get to know the saved EIP, basically I win. Why? Because the saved EIP is going to be the return address, which can be either in one library, and if I get the mapping of that library, I can find ROP gadgets or whatever inside that library entirely. Not to mention that usually in the Linux library are only translated one from each other, meaning that if you have the base address of one library, you usually have the base address of all the libraries, so in particular the libc, so in particular in protect, so I can call in protect, or your main, or your return address, if it's not in a shared library, it's going to be in your main binary. And if I find this return address, I get the base address of the main binary, and if I get the main address of the main binary, I have the PLT of the main binary, the whole executable of the main binary, and I'm back to what we know how to do, brute force, read to PLT or ROP. Enough bullshit, let's have a demo. Okay, I'm going to show you something really cool here. I'm pretty proud of it, to be honest. Yeah, larger font. Chill out. Fuck. How do you do what the? Yeah, I tried Control++. It doesn't work for some reason, so. All right. Let's first verify that I'm not bullshitting you and that the binary is actually compiled with in the state of the art. So there is stack cookie, NX is enabled, come on, NX is enabled, and the binary is actually compiled with PIE. What is this full railroad thing here? Full relocation means that, so it means two things. First off, your destructors are before the data section. We don't really give a fuck, but like in terms of, I mean, it's pretty standard when you have a BSS overflow to overwrite also the detour section and to overwrite the pointer in the detour section to point to your shellcode. In the case of a Stack Overflow, it's irrelevant, and it also means another thing, which is that your global offset table is actually going to be solved by the dynamic linker at the very moment you execute the binary, so no lazy binding. It's a bit costly in terms of performance. But then your global offset table, instead of being writable, is remapped as read-only. So you cannot, like we often do when using ROP, you cannot patch the global offset table. All right, so let me run this server here. Okay, and I'm going to run my cool exploit. Okay, so it's attacking my stuff here. All right, it brute forced the stack cookie, then it brute forced the saved EIP, therefore it finds the base address of the text. When we have this, honestly, it's game over. We could use say, read to PLT or ROP, and we would not need any kind of brute forcing. But my exploit is much cooler. Yeah, man. Let me explain you why. Let me explain you why. I actually do brute force a bit the libc because my exploit is going to work against any binary and not just that one. If I write a payload using ROP, it's going to be very specific to one application. Here, the exploit I have can target, well, assuming you can reach the vulnerable buffer, it's going to be pretty universal. So I'm going to use another server. So the one I run here was server daemon or something. We have another server here, which is server no PIE, which is not compiled with PIE. So it's definitely not the same binary. Right? The security properties are different. We don't have PIE. We don't have this full railroad thing. Well, actually, partial railroad means that the destructor section is before the BSS, but we don't have a static GOT. And we still have cookies. So let me run this application here. And I'm going to use the same exploit, again that one. To spice the stuff a bit, I'm going to run it as root. Why not? I like root shells. No PIE, yep. So I'm going to use the same exploit against a different binary. So it found the cookie, then it found that it was not compiled with PIE, so my exploit is pretty smart. And I got my root shell. Thank you. All right, so as you can see, remote Stack Overflows are not that interesting, and this is why the original tool, what we're getting back to, is actually not targeting Stack Overflows. Any question? Too easy. All right, let's go to the meat. So what I'm really interested on, to be fully honest, is not Stack Overflows because, I mean, when you do security research and stuff, you don't find that many Stack Overflows anymore. What you get a lot is invalid reads and invalid writes. Like, if you fuzz any kind of, servers or whatever, or even like local stuff, you get heaps of that stuff, like the lame Perl bug I showed you, like this compare something with 9, and the compare stuff is reading from the first page. Is this exploitable? Hard to say. So this is why we took the time to write a debugger. Jude, you don't like my talk? You're bringing me beer. I love you. All right, the basics. You already care about the basics? Yeah? All right, so quick, the basics. Why do applications crash? All right, they can crash in many different ways. Basically, you can hit an assert and it's going to abort and end up with a signal 6. You can get a stack corruption, and if it's compiled with SSP, it's going to be cooked by the handling routine of the libc. Or, more interestingly, you can have an invalid memory access, which can be of 3 different types. You can try to execute a memory location you're not supposed to execute. What's the probability that this is going to be exploitable? Your application is dying, and it's trying to execute something which is not supposed to be executed. No idea? We say that this is very unlikely to be executed, to be exploitable. Yeah, one person, 2 people, 3, all right? Who says it's like 50-50? All right, who says it's super likely to be exploitable? Well, thing is, it depends if you can actually control the location, right? But if you control the location, if the application is trying to execute a memory location it's not supposed to, and you can control this location, you make it point to some data you control, and it's game over, right? I have slides to explain this. All right. Why do bugs happen? All right, we don't really care. There are so many ways you can fuck up, like variable misuse, yeah, blame my French, heap overflows, overflows in any kind of sections. I'm especially interested in those. Like, if Stack Overflows are very well understood, and there is some literature on heap overflows, there is kind of little which is currently usable for, say, BSS overflows, especially because of what I just mentioned. Like, if you have your destructors which are before the BSS section, then in case you have a proper BSS overflow, you need to override something in this very section to achieve remote execution. And this something you're going to overwrite in the BSS section, and we're looking for, is actually called a function pointer. Same thing for heap overflows. Like, in theory, you can overwrite heap metadata. I'm assuming you have a recent ptmalloc memory management. We're not in 2000 anymore. I mean, we have safe unlinking and stuff like this. So by overwriting only heap metadata, I know in theory it does exist, but you need to be able to allocate thousands of chunks with arbitrary size and arbitrary content to achieve an arbitrary for write. This is total bullshit in real life. The real way we do exploit heap overflows is basically you find a function pointer in your heap, you override the heap. I love you, finally. You override the function pointer, and you make the function pointer point to data you control. And this is how we achieve arbitrary code execution. There's no poison in it, right? Just wait. All right. Obviously, NX is going to be a problem, but I'm going to discuss this. I have 51 minutes left. Woohoo! All right, so back to the exec thing. Imagine I have call EAX, and I have a segmentation fault in that stuff. I mean, come on, if I control EAX, this is cheesy. You make EAX point to data you control, and that's it, it's going to be executed. Or you make it point to an interesting routine inside the application. Invalid memory reads, that's pretty unlikely, actually, to be executable. There are some cases where it is. For instance, imagine this comparison is supposed to be true 99% of the time, and you can make it fail. It's going to take another branch and execute code it was not supposed to. And that's pretty bad. Yeah? Question? Nope? Oh, good. Another example of an invalid memory read, is this one. This is kind of unlikely to recognize. FLD is like a floating point instruction, so if you're not super fluent in assembly, it's not immediately obvious that this is actually a read. And PMCMA, so the tool, is going to find it for you. All right, we don't care, we don't care. I'm going to skip to the demos. We have only 15 minutes left. Any questions? If you like the joke, buy me beers. Yep.
Nowadays, data section is protected by this system.
You asking me the destructure?
In fact, on the actual distribution,
Yeah.
data is read-only.
Detour is read-only, so it depends. Like, detours, so the destruction, the detour section, which is a section which contains an array of function pointers to be called when you basically call exit. When you have what we call partial relocation, yes, it's remapped before the data segment. So yeah, it's going to be remapped as readable, but it really depends on how you compile your binary. And actually, if you're smart, you can produce a binary which has no which has no detour section at all. Like you can produce a custom linker script which removes the section entirely, or which puts the detour section between two read-only sections and is going to be mapped as read-only, which effectively means it's not going to be used at all. Good question, thank you. Any other question? All right, so let's do this cool stuff. I'm going to do a bunch of demos here. Please give your hand to your neighbor. Yeah, do it. We're gonna pray together. We're gonna praise the demo lords because it never works in real life. All right, I'm going to start with a few videos, and if we have some time, I run PMCMA on SSH, which is like the cool stuff. All right, let's start with I'm not too sure how much time I have left, so I'm going to start with that one. Yeah, it's fake, it's a movie, but I'm gonna do the real thing after, man. All right, just to show you how it works. So the idea that, because I've been asked, yeah, man, it's cool, I know. We're using the tool to prototype the exploit and not to exploit. I'm saying this because, like, I've been asked previously. Some people, dude. Yeah, it's pretty obvious that if you can ptrace attach to SSH, you're root already. So, like, PMCMA is of no help to you. PMCMA is fine to prototype the exploit, and we don't actually use it during the real exploitation stage, right? I'm just mentioning because some people got confused previously. All right. Here we go. Sorry. Here we go. So we're going to attack sudo. So I'm stopping sudo during its execution. I'm copying its PID, which is 2120 or something. And I'm attaching to this PID, 2120, asking PMCMA to list only function pointers and if it finds one, to actually exploit it. So here, it's finding me a bunch on the left of, it's telling me, hey, I found function pointers which are actually called, and the mapping of this function pointer is repeatable with 100%, which means this function pointer, in spite of ASLR, is going to be at the very same location all the time. What does it mean? Game over. If I overwrite one of those, and I make it point to my shellcode, it's going to work. People who followed should be like, what? There is one problem, actually. It's NX. Like, if you did introduce some shellcode, yeah, it should be in a writable zone, and it should not be executable. I'll get back to this after the video. Well, here it's a debugger, so obviously it's kind of working. The cool thing here is that at the end of the video, yeah, here, it should create, it should open a port on 666 and bind a shell to it. And since we are taking sudo, it's going to be run with root privileges. So let's run netcat on port 666. And we root. Woohoo! Yeah, that was a video, but that was pretty cool, so you could upload, I think. Thank you. I'm going to show you why I wrote this whole tool entirely. I actually found a cool bug in Opera. So I need to do some voodoo here. I'm going to explain the voodoo. Hey, no cheating, come on. Now, like under Ubuntu, you cannot debug your own applications. Like, yeah, I know. You need to set this particular key in the procfs file system. So I'm just going to run this as root. Now I can debug my own applications, and I'm just going to run the stuff on Opera. All right, so I'm starting Opera with PMCMA. It's fasting. All right, here we go. And I'm going to trigger the bug, yeah, that one, Opera POC, minus the size of the proof of concept. It's ridiculously small. Anyway, so Opera started. And it's crashing on this instruction. Does this look exploitable? Hey, it looks pretty good. It's a writable instruction. It's a write instruction, so maybe I can write anywhere in memory. Turns out I can. Yes, I can write anywhere in memory. Problem is, EAX is actually always null. So I can write 0 on 4-byte aligned memory anywhere I want. Is that exploitable, writing 0 anywhere? No, it doesn't look good at all. So, but it's not impossible. So let's see. Let's see. All right, so it's doing my ASLR test. I'm just showing you here that the tool can actually scale to an application to the size of Opera, even though the last stuff, yeah. So here it's gonna take forever. Why? Because basically it's gonna parse the heap, which is several hundreds of megabytes big. So this stuff is gonna take like 1 hour or something. And it's gonna find 0 exploitation pointer, because if I find exploitation pointer, all I can do, all function pointer in your binary are gonna be 4-byte aligned for compiler performance, basically. Your compiler is gonna make sure that all your function pointer are 4-byte aligned, and if you can write 0 on 4-byte aligned binary, all you can do is basically 0, 1 function pointer, and you cannot truncate one, which sucks. So plan B. Yep, 5 minutes. Thank you. Easy cheesy, no worries. No, I'm not gonna restart Opera. So what's plan B? Okay, even if I find function pointers, I cannot override them to hijack them, and I can only write zeros. So I thought like, hey, you know what? But I can still write pretty much anywhere I want in memory, and that's pretty cool. So what we're gonna do is use PMCMA to do something I find pretty amazing, which is tracing all the unaligned memory reads and writes. We do this by basically, I let you look at the demo, and which is going to trace SSH, and I'm going to explain you how it works. Basically, we set the we're gonna set one flag in the it's called the align flag in the eFlag register. So like on Intel architecture, you have this special register which is called eFlags. There is this special flag which nobody ever uses, which is called the unaligned flag. When you set the unaligned flag, every time your application is going to read or write from unaligned memory, it's going to trigger a signal 7, a SIG bus. So PMCMA is going to catch the SIG bus and set back the trace flag, and effectively I'm going to trace all the memory reads and writes inside the application. I don't know any other way to do it. And what's cool about it is that here in SSH, you can see that I find a bunch of XOR word register. I'm using a 64-bit architecture just to show off and show you that it works on 64-bit architecture. And if you want to port it on BSD, you're most welcome. Basically here, the read is unaligned. Why is that? Because of the 3 here. And here, because of the 1, right? If you take any value, you multiply it by 8, you add another register and you add 1, it's very likely to be unaligned. So this way, we can list all the reads of variables into registers which are unaligned. So if I can only write 0 into a memory, what I want to do is write at this location. Why? Because I'm going to find a variable, I can truncate it, and maybe I'm going to trigger a secondary bug inside the application. Wow. All right, one last thing, and I'm done. Hey, that's cool, eh? All right, okay, so 2 things. I'm sorry, I'm going to be a bit late. The inner working of the process is, so it doesn't work at all like GDB. What GDB does is basically you have GDB, and it's p-tracing another process, and that's it. Yeah. My debugger, what it does is you have the debugger, it's debugging its debugged process, and it's going to force it to fork. So it's going to create a replica of the very same in terms of mapping, state of variables, stack cookie, whatever, any interesting property, is going to create a clone, if you will, of the debugging process in memory. So you can repeat at will. Thing is, how do I find all the function pointers in memory? Basically, in the first offspring I'm creating, I'm overwriting the first possible variable in writable memory. In the second fork, I'm overwriting a different variable, etc., etc., etc. And I can do it n times. So the process is actually not super costly, and it is exhaustive. So that's pretty cool. I'm skipping you all the gory details. If you're interested, please go to the white paper. The last thing when I told you I bullshitted you was the NX thing, which should be... yeah, I'm on. Oh, that's really interesting too. No, okay. Hey, next year, you tell them to give me 2 slots. Yeah, that's the thing. Stack desynchronization. I thought I was a genius when I found that, and I got an email from Nergal who told me, hey, that was in my frac white paper 5 years ago. But yeah, that was a cool white paper reward, and I felt even smarter because that guy is just a genius. Anyway, the idea that, okay, NX is a problem. So instead, even if you manage to find a function pointer and overwrite it, you cannot point directly to your shellcode, because the shellcode you're going to load is going to be in writable memory, and it's not going to be executable if you have writable XOR executable. So how do you move around this? Well, the idea that if you somehow control a big buffer in the stack, what you do is, instead of returning to the normal function prologue, which has a given size, you return to a different function prologue. And what you're going to do is desynchronize the stack. If the stack expected to be, for instance, to pop 10 variables, 10 bytes before returning, and you pop 200, well, you're desynchronizing the stack. And what you can do from here is actually create a fake stack frame inside the stack itself. Wow, and that's really cool. And you can actually do that remotely. So the idea that statically, we can very well find, assuming you control a big buffer somewhere, just a sec, assuming you control a big buffer somewhere in the stack, you try to find function prologue, which actually allows you to shift the function pointer bang in the middle of the buffer you control, and from there, you can actually put a bunch of pointers to ret, which is going to act exactly like an obsled, and then you put your fake stack frame, which is going to call mprotect, much like ROP, and copy the proper shellcode in a writable zone, call mprotect, and make it executable. Yep.
How do you do pop and push on the stack? Because normally it won't execute. This is so if you have a stack segment, so it won't execute because it's a joke in this thing. You don't want to have an executable stack.
Yeah.
So you have a buffer in the stack, and you can write a push instruction and a pop instruction, but it won't execute this.
Yeah, you missed the point. I'm not doing any pop or push. I'm returning because I control. If I overwrite a function pointer, I control the next instruction to be executed. I can return to say sub ESP whatever, a very big value, pop ret. So what I do is pointing to this different epilogue from the normal epilogue. And this is going to return in the middle of a big buffer. And if I control the big buffer, then I create my fake stack frame over there. Yeah. Any other question? Yep.
Will the shown examples, including the sources to be downloaded, and if yes, where?
Anybody got the question? I missed it then. Oh, sorry. I'm going to get back to the address. Hey, thank you for helping me doing my auto-promotion, buddy. Here we go. So the source code can be downloaded on pmcma.org.
Okay.
And the slides are over there too.
So, and there's another question. It means, is there a possibility to brute force the stack cookie without having heaps of forks of the program?
So thing is, this is not about PMCMA, right? It's about the stack corruption thing. Basically, if your application is not forking, so if it's using thread, or even if it's simply not a network daemon, you're doing like local exploitation, so you're attacking sudo. Anytime you're going to execute the binary, the cookie is going to be different. Right? So there is no way to brute force it. I mean, you can brute force it in the sense you can try to find a 32-bit value, but that's really big. Like doing it in 1,000 tries is a lot smaller. This is what we do. Like in effectively, say in Ubuntu, the first byte is always 0. So the size of the stack cookie under 32-bit is actually 24 bits. There is 24 bits randomness. That's still really big. I mean, it's in millions. So you need to execute your exploit millions of times in the hope to get one working stuff. If you're attacking BSD, the cookie is always the same. It's called a null terminator. And if you're lucky, like if you can copy zeros, you actually know what the cookie is going to be. So there is zero randomness, and you can actually write a reliable exploit without any kind of brute forcing. But that's just because the way they implement stack cookies is pretty lame compared to the Linux ones. Any other questions? Thank you, mate. All right, thank you so much.